Hello again. In the last part of last lecture, I put a graph on the whiteboard. That graph showed that the cost of US ethylene fell by a factor of 3 between 2010 and 2016. We need to explore why. The why can be answered very simply. It was because a new raw material source had been discovered, specifically wet shale gas. I want to spend this lecture looking a little bit about shale gas. I want to look at some of the arguments both for and against, and I want to do so in as dispassionate manner as possible. I don't want to tell you how to think. I want to give you information based on evidence such that you can make up your own minds about a particular topic. You will already know quite a lot of things about the shale gas argument. I want to try and introduce some other pieces of information that you may not know, both on the negative and on the positive. It's up to you to make your own mind up as to whether this is a raw material that has great benefit or it's a raw material that's best left in the ground. So, we'll have a look at how the differences between ethylene production have manifested between naphtha and ethane and how that impacts the chemical industry that depends on both of those routes. So, let's start off by having a look at what shale is. Here on the whiteboard, I've put a picture of some shale. The shale in question is the Chattanooga Shale in Tennessee, the USA, and it's above ground level. This is not a shale gas area, but it does show very nicely what shale is. It's a rock. It's a mud-based rock. The muds and sediments were laid down geological timescale ago as a sedimentary rock, probably with organic matter as well. So over geological timescale, these mud layers have become compressed and consolidated into a loose porous rock. The organic matter has decomposed, and consequently in the pore structure in this loose porous rock there are decomposition products, hydrocarbons, typically methane, ethane, butane. So when we say wet shale gas, we mean methane plus what's termed condensate, higher molecular hydrocarbons that form a liquid. Now, a lot of the discussion about shale has been in respect to the US or the UK, but shale is ubiquitous worldwide. Shale gas deposits, therefore, are also ubiquitous worldwide. The map I've put on the board highlights known shale gas reserves in dark brown. As you can see, they're distributed anywhere from the Americas, through Asia Pacific, through Africa, through to the EU and Scandinavia. There are vast reserves of shale gas worldwide. The light brown regions on this map show undiscovered or unquantified shale reserves. Doubtless there are many more shale reserves waiting to be discovered. So the shale gas argument is not going to go away anytime soon. We need to become informed as to the costs and the benefits of this disruptive raw material such that we can make intelligent decisions for the future as to whether or not we should use it, and if we do use it, how we use it. I'd like to discuss with you now some of the findings of a recent review, independent from producers, independent from governments, that was carried out, that highlights a lot of the problems and some of the advantages of shale gas production. I'd like to start with the problems because these are the things that are often publicised and that you will identify with most of all. One of the key problems associated with shale gas production is fugitive methane leaks. Methane is a very, very potent greenhouse gas, and so fugitive emissions from methane wells is of huge environmental concern, and this should not be allowed to happen. The global warming potential of methane is some 40 times higher than that of carbon dioxide. So compared to conventional gas drilling sites, there have been discovered far greater fugitive emissions of methane from shale gas extraction sites. Some of this has been associated with poor engineering practice, so that can be remedied. The greater discussion of fugitive emissions, however, needs to be looked at in a lot more depth. There's been concerns over water and chemical use while drilling. In actual fact, the water use for shale gas extraction is comparable to coal extraction, to uranium extraction, and to oil extraction. The difference comes when you compare it to existing natural gas extraction. It's a lot higher than existing natural gas extraction. There have been rightly a lot of concerns about the contamination of aquifers. There have been dramatic images out of the USA of people's domestic water supply igniting because of dissolved methane coming out of solution. What gets talked about less are levels of organic carbon, radon, selenium and strontium measured in aquifers, and these are many times higher than water safety limits. So, whether this is poor engineering, poor well construction, whether it's poor well placement, whether aquifers can be totally avoided or not, needs to be explored more fully. There may well be ways of extracting gas without these problems. However, these problems should not be allowed to continue. The land use associated with shale gas can be high, some 14 to 73 times worth than some of the other options. But it has also been shown that with good practice, this land use can be reduced to be 10 times less than the land use of, say, offshore wind, or coal mining, or photovoltaics. And so again, there's a combination of the inherent amount of use required by an operation, coupled with good engineering practice. There have been a lot of reports of seismic activity around shale gas extraction sites. People have experienced earth tremors. Some of these earth tremors have been measurable on the Richter scale. But actually, this needs context, because every drilling and mining operation causes earth tremors. And the statistics show that shale gas earth tremors are virtually lower than any other mining or drilling activity. There's been a measurable decrease in air quality around some of the shale gas production sites. Again, whether this is due to the inherent nature of shale gas production or poor engineering practice associated with quickly constructed well sites is a matter for further investigation. There have also been increased incidences of bad health close to shale gas wells. Some of these instances, however, have been linked to stress and anxiety concerns. Typically, very worried residents living next to a hastily constructed well site, and the residents rightly being concerned about their health, well-being, and experiencing very, very high levels of psychological stress as a result. These are things that can be managed. The other health conditions that are physically linked to shale gas extraction under the proximity of wells needs to be investigated, and that evidence looked at very, very carefully. Some of the benefits of shale gas have been given not as much highlight as they perhaps should have been. If we think about environmental performance, if we can assume, rightly or wrongly, that shale gas can be extracted in an environmentally non-impacting manner, then if natural gas displaces coal as a power generation fuel, then actually you're reducing your greenhouse gas emissions per megawatt hour of electricity generated. There's an even stronger argument, however, that we should be using renewable resources to displace coal, and that is absolutely correct. However, gas production allows us grid stability and grid continuity because of the intermittency problem associated with renewables. When the intermittency problem associated with renewables has been solved, then the argument for gas-powered production, electricity production, falls away. There are a lot of economic benefits, of course, that shale gas brings. Job creation, both total and indirect employment, has increased in the US by some 600,000 by 2010, by 800,000 by 2015, and projected to have increased by 1.6 million by 2035. However, this is often at odds with environmental damage. The industry, of course, is very financially valuable. It's worth 18.6 billion US dollars as of 2010. But again, that can be at odds with the environmental performance. It gives countries increased energy security. Not having to rely on imported gas may change the carbon overhead of that import, but also increases your own self-reliance. Again, this can often be at odds with other factors such as the environment. An interesting thing has been how wet shale gas, ethane-containing shale gas, has impacted chemical feedstock availability. The boost to the US chemicals industry by 2020 was worth 72 billion US dollars. There had been large investment in new plant due to cheaper ethane and methane prices. Ethane for ethylene cracking, methane for syngas production. So, the debate. Should shale gas be kept in the ground? Are the environmental concerns so unsurmountable that there is no excuse to produce? Should shale gas be used? Should it displace coal? Should it be used for power generation? There's a very strong carbon argument to suggest that we shouldn't be burning any more gas than we strictly have to, and we should be aiming to reduce emissions of carbon dioxide. Should shale gas be solely exploited for the chemicals industry in such a way that ethane reserves can be used to make products that consumers desire or need? And should that be taxed in such a way to drive the green energy revolution? I don't know the answer to these. There's a lot of fuel for a lot of debate. The one thing I do know is that these debates will carry on more vigorously than ever as time continues. I would like to change attention now to what happens if you use shale gas as a chemicals feedstock. Wet shale gas contains condensate. That condensate contains ethane. Ethane we know we can crack into ethylene. Ethylene we also know is a very important fundamental raw material to a lot of the chemical industry. What I would like to do is to compare and contrast two different ethylene sources, one through naphtha cracking and one through ethane cracking. What I'm going to do is to look first of all at the chemicals produced by each of these routes. So in red there on the graph are the byproducts produced by naphtha cracking, assuming that I produce 1 unit, whatever measure you like that to be, 1 unit of ethylene. The key message here is that 1 unit of ethylene from naphtha cracking produces significant amounts of other high-value chemicals: methane, propylene, butadienes, butene, butanes, pyrolysis gasoline. Pyrolysis gasoline, remember, contains benzene, toluene, xylene, and fuel oil. So naphtha cracking not only produces ethylene, but also a very wide range of other essential feedstocks to the chemicals industry. Contrasted with ethane cracking, shown there in blue, 1 unit of ethylene derived from ethane produces very small amounts of other high-value chemicals with regards to naphtha cracking. So if you change your ethylene source in the chemicals industry from naphtha to ethane, you undoubtedly change the dependencies downstream of that cracking unit. If, for example, you have benzene, toluene and xylene processing dependent on naphtha cracking, if you change over to ethane cracking, that part of the chemical food chain disappears completely. Let's have a look at energy intensity. In terms of naphtha cracking, if you look at the specific energy consumption of naphtha cracking, it's around 25 to 40 gigajoules per tonne of ethylene, but as we've seen, naphtha cracking involves lots of other high-value chemicals, so it's more practical to talk in terms of the total energy consumption for all the high-value chemicals together, and it's between 14 and 22 gigajoules per tonne of high-value chemicals. In terms of CO2 emissions, or CO2 equivalent emissions, for high-value chemicals, we're talking about 1.6 to 1.8 tonnes of carbon dioxide equivalent per tonne of high-value chemicals. Contrasted with ethane cracking, if we look at the energy consumption normalised to high-value chemical production, there's not a lot of difference to naphtha cracking. It's still around 12.5 to 21 gigajoules per tonne. In terms of carbon emissions, however, in terms of high-value chemicals, it's 1 to 1.2 tonnes of CO2 equivalent per tonne of high-value chemicals, which is somewhere between 3/4 and almost half of that due to naphtha cracking. So if we can crack ethylene from ethane, actually, so long as the other chemicals produced by the ethane cracker are compatible with downstream operations, we can actually reduce our carbon intensity in terms of carbon dioxide emissions. So that's interesting food for thought. The picture I've put on the board now is of a large petrochemical site in Scotland. It's at Grangemouth. It's the Ineos petrochemical site. Now, this petrochemical site has been, again, in the news a lot over the last 10 years. It almost closed in 2010-2011 due to the cost of production and due to the increasing scarcity of domestic ethane derived from North Sea gas. For many years, this site was operating at 40% of its production capacity due to a scarcity of ethane. Now, the impact of US shale has been immense because over a period of years, the site owners put together a rescue package which involved importing US ethane into Scotland. This $1 billion rescue package allowed this chemicals production site literally overnight to go from 40% capacity to 100% capacity, completely revolutionising one of Scotland's largest manufacturers. In a similar way, the production site at Rafnes in Norway, owned by the same company as the Grangemouth site, received a similar investment and also was able to overnight change its capacity and change its production. Other sites have followed suit. The naphtha cracker at Wilton International, the old ICI site my friend the Ghost of Chemical Engineering Past talked to us about, has been converted to become a naphtha and a gas cracker. It's now the most flexible ethylene cracker in the whole of Europe. It can take pretty much any feedstock that you can reasonably crack into ethylene. That upgrade package has secured the future of that plant and all the jobs and employment associated with it at a cost of $300 million. So what happened? How did this come into place? Effectively, what was built was a virtual pipeline for ethane. So $2 billion of investment will buy you 4 state-of-the-art gas tankers capable of transporting cryogenic ethane across the Atlantic. It buys a 19,000-tonne cryogenic storage facility at Rafnes. It buys a 33,000-tonne cryogenic storage facility at Grangemouth in Scotland. It buys a new shale gas terminal plus all the piping and infrastructure at Marcus Hook in Pennsylvania. And again, I'll reiterate that overnight increase of capacity. It absolutely revolutionised the future of the Grangemouth site. So what I wanted to do in this part of this lecture was to explore some of the pros and cons of shale gas. The debate around shale gas will rage for years to come. One has to dispassionately look at the pros and cons and make a judgment based on evidence as to whether shale gas should go ahead, shale gas should be banned, or shale gas should be allowed in some restricted context. This is a debate for you, the chemical engineers of the future. However, in terms of key points, shale gas can be found worldwide. This raw material is not going to go away. Dry shale gas consists mostly of methane. Wet shale gas includes ethane condensate and some butane condensate and some propane condensate. It is a highly controversial raw material. Vigorous debate will rage for some time around the pros and cons. In terms of chemicals production, ethylene produced from ethane has some improved environmental metrics, but also a completely changed portfolio of high-value chemicals which will affect any downstream processes. I've given you an example of a multi-billion-dollar investment that's already taken place that has allowed US ethane to revolutionise parts of the EU and Scandinavian chemicals industry literally overnight.